So then following on from that, obviously we can use different representations for acceleration, again, depending upon the variables that we have and the final destination. So obviously we know that acceleration is dv dt, okay? And we're going to use that if our variables are in terms of t and v, regardless of which way, okay? If, however, our variables are x and v, well, another form of our acceleration is equal to v dv dx, so we might use that form. And similarly, if we have in terms of x and v, a function in terms of x, we might use d dx of a half v squared. All right, so it's just a case of a little bit of practice in terms of identifying what form we want to use. So if we have a quick look at this first one here, v squared equals 4 minus x squared, find the acceleration. Now I guess it's really just noticing here that v squared, so don't forget that's really saying if we take the derivative of a half v squared with respect to x, we get the acceleration. So I've got v squared, so if I work out a half v squared, just divide both sides by 2, and then take the derivative of both sides with respect to x. I've got d dx of a half v squared on the left-hand side. By definition, that's equal to the acceleration. And the derivative of 2 minus a half x squared is just negative x. So there's my acceleration in terms of x. Then obviously at x equal to 1, my acceleration is negative 1. We probably should put in a meters per second squared there to finish that off. Okay. Or, okay, let's have a look in here. We've got an object falling, helicopter hovering above the ocean 1,000 meters above sea level. So there's my position initially. Falls from a hovering, so the initial velocity is 0. We're not up or down. Find the velocity of the object when it hits the water, neglecting air resistance. So neglecting air resistance suggests we have constant acceleration. So I'm going to take acceleration. I'm going to add downwards as my positive. Okay, so acceleration is 9.8. I could go to kinematics formulas, definitely, but my velocity is, so acceleration is equal to obviously dv dt. So if I integrate both sides with respect to t, 9.8 t, initial velocity was 0, so velocity is just 9.8 t. Differentiate that again, I get x equal to 4.9 t squared. I'm 1,000 meters above ground when it initially is dropped, so d is 1,000. So there's the position, rule for the position of the particle at any point in time. Find the velocity of the object when it hits the water. So when it hits the water at x equal to 0, if I then solve for t, I get 1,000 is equal to 4.9 t squared equals, I'm going to turn it into a half g here just to save mucking around with 4.9s. If I do that, I get t squared is equal to 2,000 on g. Take a bit of a square root, 2,000, 400 times, what's that, 400 times 5, so 20 root 5 on g. Okay, just to leave it in an exact form. I guess we could have got a decimal equivalent, but it works out quite nicely to work with that form of the equation. So that's the time that it's going to hit the ground. So what's the velocity at that point in time? Well, the velocity is just 9.8 t plus c, which is just 9.8 t. So 9.8 is, of course, g. Okay, so really we're saying the velocity is equal to gt. And so if I substitute t in there, I can group my g's, g to the minus a half, g to the half. So I get the square root of 5g, 5 times g, 9.8 times 5 is 49. And so we can get a nice little square root of 49 there, which gives me 140 meters per second. Since it's positive, that's in a downward motion. So I just need to state a direction. So I'm going to say 140 meters per second down, okay? If we have air resistance, well, obviously we can't use our kinematics rules. So my acceleration instead is g minus 1/5 of v squared. So again, accelerate. Let's just tidy it up a little bit. We'll divide everything by 5. So g times 5 is 49. So 49 minus v squared on 5. Now, what's a form we're going to use here? So if I could use dv/dt and get it in terms of t, and then muck around and getting in terms of x. But at the end of the day, I need to have the x. I want the velocity at a certain point in time. So it kind of makes sense to get myself a rule in terms of the velocity. So let's write the acceleration as v dv/dx, okay, equal to 49 minus v squared on 5. If I flip everything, so that becomes dx dv here, 1 on v on the left-hand side. If I multiply it across, it comes onto the top on the right-hand side. I've got to flip this one here to get me 5 on 49 minus v squared. That v that comes across now gives me a nice little derivative of the bottom is in the top. So I guess what we're really going to do in here is I'm going to bring a 5th out the front. I'm going to bring a 5 out the front, 2 out the front because the derivative of the bottom is 2, so I end up with 5 on 2 natural log of the bottom, which is 49 minus v squared plus some c. Don't worry about that so much, we just noted that point. Initial condition, I might put it in this place. We may have put it in later, but I want x equals here. I'm not going to transpose. I will transpose, but anyway, I'll leave it like this for now. So if I put x equal to 1,000, v is equal to 0, I get c is equal to 1,000 minus 5 on 2 natural log of 49. So if I put that in together, let's bring the 5 on 2 as a common factor there. So there's my c value there, negative 5 on 2 natural log of 49, plus 1,000 at the end. Log, same base, subtraction, I divide. So I can bring the 49 in underneath the log, the 5 on 2 at the front, because they were both being multiplied by that, plus 1,000. So there's the rule for x. I'm looking for the velocity of the object when it hits the water, so I want to solve for v. So I could do one of two things. I could put x equal to 1,000 here, because that's how far the particle's got to travel. Instead, I've transposed first, so I'm going to have, minus 1,000 multiplied by 2 on 5 equals the natural log. Then I'm going to take everything to the power of e, so there's that expression to the power of e. Bring this 49 across to here, so I get a 49e to the x sort of thing. Bring the v squared over, take the other term back, so I get v squared equals 49 is a common factor, 1 minus e to the power of, written a little bit small there, 2/5 of x minus 1,000. So there's my v. All right, now at x equal to 0, if we put x equal to 0, I get v squared equals 49 times 1 minus e to the power of negative 400. Well, e to the power of negative 400 is going to be 0. So I get v squared is equal to 49. So the velocity squared is 49, v is equal to plus or minus 7. My particle is falling, so I'm either going to say it's negative 7 meters per second, or, just to be consistent with the other one, I might say, or 7 meters per second downwards, as long as you give a direction.